All right. Good day, everyone. I hope you're all keeping well and keeping healthy. Today, um, as a reminder, the chapter 5 and 6 assignments are now due tonight. So you have until midnight to finish up the homework, the quiz, and send in your lab. So shortly, I'll open up any questions anyone has for those. The chapter 7 assignments are also live, so do be working on those. Those are currently due next Tuesday. So, um, other than opening up the floor for any questions that you guys have, we'll just keep moving forwards in the chapter 7 notes, talking about thermal energy, and we're going to start off at least with how thermal energy factors into temperature. We'll keep working on the chapter 7 assignments over the weekend, and keep as a reminder, test 2 is on the horizon in the next couple of weeks. Test 2 will be on chapters 5 through 8, everything sort of pressure and thermal energy related. So I think
Now-
that's it for announcement. Oh, sorry.
Is that the conclusion of this course? Of
Not
1000?
in it. Not in its entirety. I have planned to go over 2 additional topics after chapter 8. If for no other reason than they are about waves and electricity, and those are important things to be able to understand, given that electricity runs our world and you see and hear everything because of waves. So in the weeks between test 2 and final exam prep, those are going to just be some additional topics that we won't spend a huge amount of time on, because there won't be a dedicated test for them. There will not be a chapter 9 and 10 test. And I don't want to take, I want us to be able to review the exam in the last week before the actual exam is taken. So there will be some extra stuff.
All right. Oh, he's gone.
Still having fun. Oh. Yeah, so me and your mommy was playing a roller coaster game. And I was already on the door. No, but you did ride it back. Did you want to go on the game? Yeah. It's a 1 hour wait. But who gets you with me? Come on, gentlemen. Oink. Oink. Good night. I love you. Yeah. I can't wait to play the roller coaster game. Oh, yes, you can. You gotta be this tall. And there.
Okay, am I back?
Yeah, you're good.
Okay.
I gotcha.
The Wi-Fi in Richardson has been awful lately, as you probably could guess, and it's a big problem when it causes the calls to drop, and sometimes it causes me to lose the meeting codes. So, as an additional announcement, we are still on track to resume normal class meetings next week, still exercising all caution. So, hopefully the internet won't be an issue anymore after that. As a reminder, test 2 is coming up in the next couple of weeks. I'm expecting it to be around the tail end of the first week in November. So around November 4th through the next weekend. Sorry, through the weekend, just to give you guys the same amount of time to do it as the last one, which leaves us about 2 weeks for the additional materials and also for exam review. So we'll probably do chapter 9 and 10 in a couple of lecture calls. It's not a lot of information. It's just stuff I think you guys should know to be able to understand how it affects the world around us. So we'll spend a week learning about those, and then we'll move on to exam prep. And then the exam itself will take place, I think, from the 22nd through the 25th, and then Thanksgiving, and then we're done for the year. So the test 2 is fast approaching, and so too is the end of the class. So make sure you have all of your old materials to be able to review them. Any other questions about the class, the coming weeks, or any of our assignments before we continue with chapter 7 today? Excuse me. All right, so if you have any questions about any of the materials, do speak up at any time. Today we will continue talking about thermal energy. I believe we left off talking about thermal contact last time. And so when two objects are in thermal contact with one another, that is when thermal energy is able to transfer from one object into another. And there's 3 different ways that thermal energy can transfer. So I guess you could say there's 3 different kinds of thermal contact. If you move on to slide 6, I'll just share screen so that you know which slide that is. We're going to talk briefly about the 3 methods of heat transfer. There are 3 of them. And you have interacted with all of them before. If you have not learned these terms, you will have at least dealt with all of these methods. So, the most straightforward method is conduction. And conduction is simply when 2 objects are touching and thermal energy transfers between them. So, conduction. So, what I'm drawing here is cube A is touching cube B. Because they are touching, their particles can collide with one another, and thermal energy will transfer through those collisions from one object into another. For heat to conduct between 2 objects, they have to be physically touching. So direct physical contact, so that the particles of one can be involved in collisions in the other. Through those collisions, work is done, energy is transferred, and that energy is always going to go from the hot object into the cold object. So I'll go ahead and further label object A as the hot side and object B as the cold side. Because thermal energy always goes from hot to cold. Conduction of thermal energy is actually very similar to the conduction of electricity. If you've used the word conduction to describe electricity before, that's because because thermal energy and electricity can both travel between different objects due to physical contact. The way that heat transfers is actually very similar to electricity, and more often than not, if something conducts electricity very well, it will also conduct heat very well and allow heat to travel through it very quickly, like metal. So, conduction is very straightforward. The 2 objects involved must be directly touching one another. The next method is kind of like conduction, but with extra steps, and that's convection. So, I'm going to draw your attention to probably a very specific time of the year that's coming up, and I want you to recall cooking something in the oven. I'm going to specifically draw a turkey. So let's say you are cooking big old turkey in the oven. And usually when you try to cook something in the oven, you put the food in, you'll turn the oven on, and at the bottom of the oven, if it's an electric oven, like most of mine have been over my life, you might see some red hot coils, electric coils on the bottom start to turn red. These coils are hot. They have thermal energy. They have a very high elevated temperature. But they're not touching the turkey directly. You don't put the food on the coils. The coils are at the bottom of the oven and they're probably filthy. So if these are not directly touching one another, thermal energy cannot conduct from the coils directly into the food. So how does the turkey get cooked? Because there's two other ways that thermal energy can transfer, and you might have heard ovens referred to as a convection oven because ovens are built around the principle of convection. You see, the coils aren't touching the turkey, but they are touching the air, and that air is also touching the turkey. So thermal energy from the coils will transfer into the air. And the thing about air is, about any fluid is, when it gets warm, it tends to become less dense and start floating. There's a phrase that you might have heard before, that hot air rises. When air is warmed, when any object is warmer, its particles have more thermal energy. They tend to bounce around and become farther apart. In doing so, that object becomes less dense. So hot air is less dense than cold air, which means that hot air will float in cold air. So when you warm up air, it tends to rise. This is why the attic is usually the hottest part of your house during summer. All the hot air is naturally risen up to that point. So air warmed by the coils is going to rise, and then it will touch the turkey. Now the turkey is touching hot air. Thermal energy will transfer from the air into the turkey. So now the turkey gets warm, and now that the air has lost that thermal energy, the energy has basically leapt from the coil into the turkey via the air. Now that the air has lost that energy, it's now colder, and it will sink back down to the coils as more hot air rises. Once it's touching the coils again, it'll get hot, it'll rise again until it touches the turkey and cools down and sinks again. These are called convection currents because it's like a flow of current. You have a constant loop of hot air rising and cold air sinking, and that just circulates thermal energy throughout the oven. You might have actually felt this yourself if the oven was on and you opened it and you feel a hot rush of air come past you. That's because you've given the hot air a new place to rise to when you open the oven. So this happens in all fluids. Convection requires a fluid medium. And remember, fluid can mean gas or liquid. Obviously, this oven is designed to work using a gas, but you also form convection currents whenever you put a pot of water on the stove to boil. So we have a pot, it's probably touching a red hot electric coil. Excuse me. So this is just the heating element in your stove touching the bottom of the pot. Thermal energy is going to conduct from the coils into the metal. It'll conduct from the metal into the water. Once the energy is in the water, hot water will rise and cold water will sink. And this will also form convection currents, which help to cook whatever you're boiling in the water. It's usually noodles. So, convection requires a fluid medium that can be a gas or a liquid. And it's basically conduction with an extra intermediary step. Things still have to be touching one another. Another thing to note, though, is that via convection, thermal energy can only rise. Because convection currents have the hot fluid rise and the cold fluid sink, thermal energy can only go physically upwards because of convection. If you had a fire roaring and you were beneath that fire, somehow, let's say you had the fire like up on a plinth or something, hot air would rise away from the fire, but if you are beneath the fire, you won't receive any of that heat. Something beneath these heating coils won't get as hot because the hot air will rise past the coils. So, again, convection has a few caveats, requires a fluid medium, and the thermal energy can only rise through this method. The last method is radiation. And I'm going to draw your attention to a different specific example. I'm going to do a quick representation of the sun and the earth. The earth is apparently egg-shaped. The sun is an oblong. The sun warms planet Earth. We get light and energy and warmth from the light of the sun. Now, the sun and the earth are not directly touching one another. If the sun and the earth were directly touching, the earth would just be physically right here in physical contact with the sun. And that isn't the case because we would be on fire, among other problems. If we're not touching the sun, then we're not getting all of that thermal energy through conduction. And space is empty, which means that there's no fluid medium for heat to convect from the sun to the earth. There's no fluid medium for thermal energy to transfer through. There's no water or air for thermal energy to travel through to get from the sun to the earth. Which raises the question, how do we get that thermal energy from the sun? And the answer actually came back in the first thing I said about the sun. We are warmed by its light. Light is a form of radiation. And the sun has a bunch of energy. Some of that energy becomes light, is given off as light radiation. That radiation is able to travel in any direction through the vacuum of space. And when that light strikes its target, that light will be absorbed as thermal energy. So whenever you are standing in light, like me right now with these lights on, that light is striking my body and I am absorbing thermal energy from that light. So this energy gets from the sun to the earth through the method of radiation. All forms of radiation, and light is a type of radiation. So I want to go ahead and make that clear. Light is a type of radiation. Anytime radiation strikes something, that radiation can be absorbed as thermal energy. So all the light from the sun strikes Earth, and that's how we get the heat from it. You can also see this particular case in heat lamps at a restaurant or in GDH. Sometimes after you've plated up the food, it needs to be sitting out in the open waiting for people to get it. And if it's already on a plate, then it might get cold. So you put it under a heat lamp. The light from the heat lamp, it's not just normal light. It's also got probably some infrared and UV in it that makes the food warmer. The literal radiation from the lamp adds thermal energy to the food without having to touch it. So anytime light or another form of radiation is transferring the energy, that method type is called radiation. And so these are the three ways that thermal energy can transfer. Now, if you turn with me to slide 7, all thermal energy attempts to transfer from one object into another so that the objects in question can eventually reach a state of thermal equilibrium. Thermal equilibrium is just a fancy way of saying the two objects are at the same temperature. If I am warm and my bottle of ice water is cold and I am touching this bottle of water, I am at a higher temperature than the bottle of water, and so thermal energy will transfer from my hand into the water bottle, because thermal energy always goes from hot to cold, and this will keep happening until we are at the same temperature. Once our temperatures have normalized and we have reached thermal equilibrium, then our particles, the particles of my hand, the particles of the water bottle, would be moving at the same speed, and therefore any collisions between them would not have a powerful effect on whether or not energy was transferred between us. When two objects at the same temperature touch, they're in thermal equilibrium, and there won't be any net flow of thermal energy because it doesn't really have anywhere to go. It always flows from hot to cold, so at the same temperature, there won't be any flow of thermal energy. Now, thermal equilibrium happens when objects are at the same temperature, so let's talk about temperature and how we measure it. Now, you've been checking the temperature most of your lives. You usually know what temperature it is outside. You take your own temperature when you're sick. So you've been measuring it. I realize a lot of this coming information is not new, but the first thing we're going to do is talk about temperature scales and what they are used for. Temperature in general is how we measure the average thermal energy level of an object. And I say average because two objects at the same temperature might have different amounts of thermal energy in them. For example, let's say we have a small cube of ice in comparison to a giant cube of ice. They're both ice, so we're going to say that these are both at the same temperature. Physics and most methods of science prefer to use Celsius over Fahrenheit. So the temperature at which water freezes in Celsius is 0 degrees Celsius. And so these two blocks of ice of varying size are at the same temperature. That means they are in thermal equilibrium. Now, do these blocks possess the same amount of thermal energy? The answer is no. And the answer is no because this block has a lot more mass than this block. They're both ice, so the bigger one's going to have the larger mass. The more mass you have, the more thermal energy you need to be at a specific temperature. Because this is larger, it has more particles in it with enough energy to be moving around and maintain this temperature. Now, if we were to take one sample particle out of each object, so we just say rip one atom out of each. If they're at the same temperature, each of these individual atoms should have the same thermal energy level. So when two objects are in thermal equilibrium, their particles will be moving at the same speed. They should have the same thermal energy level. But an object with more mass has more particles in it, meaning it has more thermal energy in it. So The general rule is temperature is a guideline for the average thermal energy level of all of the particles in an object. Just because something is at a higher temperature than another object does not mean it possesses more thermal energy than another object due to possible differences in mass and density. Just something to keep in mind. Temperature measures the average thermal energy level of an object, not its total thermal energy level. We will talk about how to find total thermal energy later. We're starting with temperature because we need temperature to tell us thermal energy level, and because you've been measuring temperature, so it's a good place to start. Move with me to slide 8. Talks about a lot of the information I just mentioned. Slide 9 shows the 3 temperature scales that we're going to be using in this class, and I'm going to explain them one at a time. Temperature is how we measure average thermal energy level of an object, and so we have invented 3 different units of temperature and I'm going in order of decreasing familiarity to most Americans. Here in the United States, when we the temperature outside, or we look up what a human's temperature should be, that is usually measured in Fahrenheit. So Fahrenheit is a measure of temperature. The unit is degrees Fahrenheit, and the scale was invented by a man named Gabriel Fahrenheit, and Gabe decided to base his temperature scale around water, but Gabe chose very weird numbers to set various points to. In the Fahrenheit scale, water boils at 212 degrees Fahrenheit, and it freezes at 32 Fahrenheit. No one knows, at least I don't know, why Gabe chose these particular numbers. The scale works. This is, I guess, the imperial unit of temperature. But because the numbers here are so wonky, there's 180 units of degrees between these 2 points. A different scientist came along and invented a scale and then it works in smaller, more manageable increments. This scale was invented in like the 1850s, and not but a couple of decades later, a different man named Anders Celsius invented his own scale. And this scale was designed specifically to make the boiling point of water 100 Celsius and the freezing point of water 0 Celsius. This nice even distribution of 10 tens makes Celsius the preferred unit, at least preferred over Fahrenheit to most scientists. They both measure temperature, so you can convert directly from one to the other. Those conversions are as follows. Temperature Fahrenheit, and these equations are on slide 10. This first equation is on slide 10. If you're going from Celsius to Fahrenheit, your formula is going to be temperature Fahrenheit is equal to 9/5 times your Celsius temperature, end parentheses, you're multiplying Celsius by 9/5, and then adding 32 to that result. So if you plug a Celsius formula in here, this will give you the Fahrenheit formula. Just for your own benefit, I'm going to go ahead and show you what the reverse of this is. If you wanted a Celsius temperature from a Fahrenheit temperature, you would do 5/9 times, open parentheses, the Fahrenheit temperature minus 32. These equations are direct reverses of one another. You just take this first formula, solve it for TC, and that's what this formula is. They're just reverses. And you can use these formulas to freely convert from one to the other. If you plug 0 Celsius into this formula, it will give you 32 degrees Fahrenheit. If you plug 100 Celsius into this formula, it will give you 212 degrees Fahrenheit. So this is boiling. This is freezing. And for a good long time, Celsius became the official temperature unit of science until a different scientist came along with a new discovery. Temperatures can get colder than 0 Celsius. This is the temperature that water freezes at, but the world can get colder than 0 Celsius, right? Water will freeze at this point, but it can then get colder. We've had days in South Carolina where the temperature was below freezing. They're rare in this part of the world. If you're from further north, you know exactly how cold it can get. And so this is not the coldest temperature that exists. That means that thermal energy levels can get lower than this. A block of ice at 0 degrees Celsius still has thermal energy in it. It can get colder, which means you can remove even more thermal energy from it. This is not the coldest thing that exists. It was found by Lord Kelvin, the scientist who developed this particular train of thought, was named Kelvin and apparently had an official title. So Lord Kelvin came to the conclusion that in the Celsius scale, the coldest possible temperature was 273 degrees Celsius. This is the coldest that anything can get. Around here, we very, very rarely have like -5 degrees Celsius days. This is colder than the depths of space. This is the coldest thing that can exist. And I don't actually know what it is in Fahrenheit. I think it's 480 something. Absolute zero. Okay, I'm slightly off. The coldest possible temperature in Fahrenheit is negative, around that up to 460. So again, these are the same temperature, just different scales. This absolute lowest temperature is called absolute zero. This is the coldest anything can ever get. This is the point where an object has no thermal energy left in it at all. And since this is this temperature, and since we needed a temperature scale that better reflected how much thermal energy an object had, we needed a new unit. And so Lord Kelvin came along and, just like all these other scientists did, named a new temperature scale after himself. That temperature scale is Kelvin. We've had degrees Fahrenheit, degrees Celsius, and now we have kelvins. Lord Kelvin basically Celsius scale and adjusted it to better reflect absolute zero. So absolute zero in units of Kelvin is 0 Kelvin. 0 Kelvin is absolute zero. Meanwhile, water freezes at 273 Kelvin and water boils at 373 Kelvin. Now, these numbers might look a little bit strange, but they are just, the Kelvin scale is the Celsius scale, just shifted by 273. Notice there's 273 degrees between absolute zero and freezing, and then 100 degrees between freezing and boiling. It's the same with Kelvin. The difference between absolute zero and freezing is 273, and then there's a difference of 100 between freezing and boiling. The Kelvin scale was based on the Celsius scale, and so their degrees have the same size. 1 degree Celsius is the same size as 1 Kelvin. If a temperature increases by 1 Kelvin, it'll also increase by 1 Celsius. The only scale that does not follow this rule is Fahrenheit. 1 degree Celsius is equal to about 1.8 degrees Fahrenheit. So there's only really an equivalency between these two scales, and that's by design. And since Kelvin better reflects the actual thermal energy content of an object, Kelvin is the preferred metric unit for temperature, which means most of our formulas are going to take kelvins. One minor thing you might have picked up in the way that I'm pronouncing everything. The unit of kelvins is just Kelvin. It's not degrees Kelvin, it's just Kelvin. Notice I haven't been drawing any of the little degree circles here. I haven't been saying degrees Kelvin. For some reason, it's just Kelvin or kelvins. Not degrees, but just Kelvin. So if you picked up on that, that's why I'm doing it that way. And there's one formula to convert between Celsius and Kelvin, and it's a very simple formula. Temperature in Kelvin is equal to the Celsius temperature plus 273. That's it. To go from Kelvin to Celsius, you just add 273. So these are our 3 temperature scales in increasing order of metric friendliness. Kelvin is now the official metric unit. Celsius does still see some use. Celsius is still useful because 1 Celsius is still the same size as 1 Kelvin, which means some of our formulas can accept degrees Celsius, but your best bet for any math we do involving temperature, your best bet is always kelvins. None of our metric formulas are designed to take degrees Fahrenheit. If you are given Fahrenheit, you are likely going to need to immediately convert it to one of these other units. Any questions so far? Okay. I'm going to share screens now. So if you're moving with me through the notes, the temperature scales are listed on slides 9. The formulas for converting between them are listed on slide 10. Slide 11 is a point we already made today. Just because 2 objects are at the same temperature doesn't mean that they have the same thermal energy level. An object with more mass would need more thermal energy in order to be at the same temperature. So the example here is 1,000 cups of coffee would have 1,000 times more thermal energy than 1 cup of coffee, even at the same temperature. Now, slide 12 is about converting between temperature scales. So we list 3 specific temperatures here. We're looking at 45 units in each temperature scale. Again, notice that I did not write 45 degrees Kelvin. It's just 45 Kelvin. And I advise you to try these by yourself to make sure that you are able to convert between the temperature scales. The formulas are very straightforward algebra. You just plug the old temperature directly into the new one. And the answers are on the next slide. Please note that if we're just looking at what each temperature sort of represents, 45 degrees Celsius is a very hot day. 45 Celsius translates to 113 degrees Fahrenheit. That's the heat of the desert, possibly. Although sometimes in South Carolina, it definitely feels like it's 113 degrees Fahrenheit. 45 Celsius is the same as 318 Kelvin. Meanwhile, 45 degrees Fahrenheit is a very, very cold day. That's only about 13 degrees above freezing in the Fahrenheit scale. That equates to 2 degrees Celsius and about 280 kelvins. So 45 Celsius is hot. 45 Fahrenheit is cold. Meanwhile, 45 Kelvin is a huge negative temperature in both of the other scales. 45 Kelvin is colder than anything you will ever experience. If you are anywhere remotely near a region of space that is at 45 Kelvin, you will be a solid block of ice in an instant. That is unfathomably cold. No point on Earth naturally gets to a temperature that low. We've only been able to induce temperatures that low on planet Earth in very specific enclosed laboratory settings. So I recommend you look at these conversions, make sure you are able to convert and get to these correct answers. Moving through the slides. Thermal energy can transfer through 3 different ways. The transfer of thermal energy, the flow of thermal energy, is referred to as heat. That means that thermal energy and heat are not synonyms. And this is something that I have to fight with myself to make sure I get it right whenever I'm teaching. It's very easy to just call the thermal energy heat. But heat is actually an action. It's not the energy itself. The flow of thermal energy is called heat. You can feel heat in thermal energy leaving or exiting your body, but thermal energy is the energy type, and heat is the energy transfer. That's just a difference to be aware of. Heat always travels from hot to cold. Thermal energy goes from hot to cold. And because thermal energy is a type of energy, it is measured in joules. We're now on slide 15. Thermal energy is measured in joules. So joules is the metric unit of all energy types. You may, in some cases, see calories used as a unit of thermal energy. This is very similar to, this is basically the same thing as the calories in your food. It's another form of energy. Heat is, 1 calorie is specifically a specific amount of thermal energy. There's a direct conversion between joules and calories. Most of our formulas, all of our formulas are going to take and interact with the units of joules, but just be aware, calories are a unit that does come up. And one calorie is the amount of energy that is needed to raise the temperature of 1 gram of water by 1 degree Celsius. Moving on. These slides tend to repeat themselves a lot. Heat transfer. Heat will flow from hot to cold. All right. Now, we're going to end today looking at slide 17. I'm going to introduce this formula to you so that you have access to it as you begin working on your Chapter 7 assignments. This formula is the specific heat formula because it tells you how much thermal energy must leave or enter an object to change its temperature by a specific amount. So Q is the variable for thermal energy. Previously, we had KE for kinetic energy, GPE for gravitational potential energy. The unit we're going to use for thermal energy is a big capital Q. I'm not sure why. I'm not sure why this is the unit used. But this is the thermal energy that is added to or taken away from an object because that does specifically refer to a change in thermal energy. That does make it heat. It's thermal energy entering or exiting an object, a change within that object. Now, if you want to change an object's temperature by a specific amount, so you have a specific object with a specific mass, and you want to change its temperature by a specific amount, so that's delta T, you're going to need to add or take away a specific amount of thermal energy to make that possible. So this formula tells us you must change the thermal energy level of an object by a certain amount to make an object of a specific mass change temperature by a specific amount. Now, the way that this formula knows what kind of object you're talking about is this letter C in the formula right here. This C refers to the specific heat of a type of object. Specific heat just tells you for a certain kind of material. There's a table listed on this slide. You have iron, aluminum, carbon, water, things like that. This specific heat tells you how much thermal energy that kind of object needs in order for its temperature to change. Different objects require a different amount of thermal energy to increase their temperature by a single degree. And so, because every object has a different one, there's a table right there on this particular slide that tells you what the specific heat of lots of different materials is. So you will either be given the specific heat that you need in a question, or the question will be about discovering what specific heat an object possesses. And we're going to go over this formula in more detail tomorrow. We're going to work some examples with it, talk about it some more. And just wanted to go ahead and show you and give you a base description so that you can sing it if you begin looking at your homework today. We will continue with this tomorrow. I foresee us finishing all of Chapter 7 tomorrow, so do be looking at your Chapter 7 assignments. They are presently due next Tuesday. We have reached the end of the official lecture period. Does anyone have any questions about any of this material at all for the book right now?
Oh, I have a homework question though.
Okay.
Let's think it's for chapters 5 and 6. It's question number 8.
Okay. Five and 6 homework, question 8. Come on, Wi-Fi. Okay. So this is specifically about homework problem This is homework 5 and 6, chapter 5 and 6, which is due tonight. This is homework problem number 8. This is a buoyancy question. So if you've ever been swimming and tried to shove an object that normally floats under the water, like a pool noodle or a beach ball, you probably noticed that it takes a lot of force to actually push it beneath the water.
Yeah.
Now, what this problem gives you is it tells you how much force is needed to make the ball completely submerge within the fluid. So the entire object is under the water with a specific known amount of force, and you are ultimately asked to calculate the diameter of the ball. You are given the density of water, the density of styrofoam, and the acceleration due to gravity. So this is a buoyancy question, which means you're going to need the buoyancy formula. The buoyant force is equal to the density of the fluid that you are being submerged in times the volume of the object times G 9.8. So you know the buoyant force, you know the density of the fluid, and you know 9.8. So this formula can tell you the volume of the object, the volume of, this is a beach ball. So that you can calculate the volume of this beach ball. Once you know the ball's volume, you're going to need to work backwards to find its radius and then find its diameter. So the first thing you should solve for is volume. Find the volume of the ball. Once you have the ball's volume, look, and you have my permission to look up this formula. There's a formula that will tell you volume of a ball, of a sphere, is equal to, you know what? It's not a good sign that I keep forgetting this conversion. So volume of a sphere. It's a good thing. One of the reasons I give you formula sheets is because I don't remember the formulas half the time. So this is the formula for the volume of a sphere. This is considered generally known, so it's fine for you to look this up anytime. Volume of a sphere equals 4 over 3 times pi times radius cubed. Once you find the sphere's volume, you can use this to find the sphere's radius, and then radius is half of the diameter. So find the volume, find the radius, multiply the radius by 2 to get diameter.
So it's radius cubed. So when you square root it, how you square root that again? Because you can't just.
So it's technically not a square root. It works the same way, but it is a cube root. I'm going to fish out my calculator here.
Yeah, I didn't know how to type it in on the calculator.
It's all right. If your calculator is at all similar to mine, powered on, the square root button is you would hit second, and then you would hit the squared button to get to the square root function, but you need the cube root function. So you're going to want to hit math, and right there, option number 4 on mine is cube root. That is, it's like square root, but you're finding it, you're undoing a to the third instead of a to the second. So you can just scroll down and select cube root, press enter, and that puts the operator on your screen. And now you can type whatever you need to take the cube root of in there.
All right, thank you.
You're welcome. Anyone else have any questions today before we break from this meeting? Okay. We'll have the H lecture is going to begin at 12. You guys are welcome to join that. We're going to be going over the same, and then the last parts of. You're welcome to attend any lecture you want. We have the H lecture at noon, and also the lab hours, office hours at 1:30. You're welcome to hop in and out of either of those as you please. If you don't have anything for me right now, please hop into those sections with any questions you have at any time, or email them to me at any time. And if I don't see you again today, have a wonderful day. Thank you guys very much.